Today we're going to talk about tangential velocity. We're going to go into a little more detail about this since tangential velocity plays a huge role in the Ohm particle model. In particular, we're going to talk about how to apply modified unit analysis to the problem of tangential velocity. Now, as you may recall, the tangential velocity is the velocity of a point on the outside of a spinning circle. So you can imagine that this is a spinning disk, and the tangential velocity is the basically linear velocity. If the particle here, let's say you were on a spinning disk and this particle was somehow freed from the spinning disk, then this is the velocity it would be going, and of course this is the direction it would be going. This is referred to as the tangent of the circle, and the particle would is basically moving in this direction at the tangential velocity. So first we're going to talk about the difference between standard unit analysis and modified unit analysis. And these are the terms that we will need to solve the tangential velocity problem. And so in standard unit analysis, frequency has units per second, has the units of hertz, which is s to the -1, so the inverse of time, basically. Angular frequency also has the units of the hertz, which is s to the -1. Lambda, which is wavelength, which is also the circumference of the circle, in standard unit analysis has the units of the meter, and radius as well in the standard unit analysis has the units of the meter. So the units of frequency and angular frequency are the same in standard unit analysis. The units of wavelength and the circumference of the circle and the radius are also the same in standard unit analysis, and the value 2 pi is unitless in standard unit analysis. In modified unit analysis, the units of frequency are cyclic frequency are cycles per second. The unit of angular frequency is radians per second. The units of wavelength and the circumference of the circle are meters per cycle. And the units of radius are meters per radian. And the unit, 2 pi is not unitless in modified unit analysis. In modified unit analysis, 2 pi has the units radians per cycle. So what we're going to do is we're going to solve a problem, and I'm going to solve it two different ways. One using standard unit analysis and one using modified unit analysis. So I want you to imagine a disk that is spinning about an axis. The rate of spin is 2 revolutions per second, and the radius of the disk is 1/2 meter. So the question is, what is the tangential velocity of the spinning disk? So the first thing I do, because I'm not very good at word problems, I've never been very good at word problems, and so the first thing I do is I draw a picture of a disk just to give me a visual of what the problem is about. And then I write down what I know about tangential velocity. And so I often will do it in words just to wrap my head around what is going on. And so the velocity, the tangential velocity, okay, the tangential velocity, I'm just going to do that for now, just to remind you we're talking about tangential velocity, is the radius of the disk times the frequency with which it is spinning. The next thing I do is I write down the units, because unit analysis is very important in trying to figure out whether you are solving this problem correctly. And so in standard unit analysis, the units for radius is the meter, and the units for frequency is hertz, or the inverse of time, or s to the -1. And of course, these work out to be the units of velocity, and that's exactly what we want. We are talking about a linear velocity, and the tangential velocity is a linear velocity with units meters per second. So now it looks like we have all the information we need to solve the problem. So you go back to the problem and you go, okay, so the rate of spin is 2 revolutions per second, and the radius is of the disk is 1/2 meter. So one might be inclined to do this. One might be inclined to plug 0.5 in for the radius and 2 in for the frequency and get 1 meter per second for your answer. If this was a question on a test, you might even pat yourself on the back and be quite sure that you are going to get perfect on your test. But then you get your test back and there is a red X through your answer. This was not the right answer. And so, so now what we're going to do is you start all over again, but this time we're going to use modified unit analysis. So we start out the same with the question, and then I draw a circle to represent the disk, and I write down the formula that I believe is the equation for solving the tangential velocity of this spinning disk. And so this time I'm using modified unit analysis. And so I write down the units for the radius, which is meters per radian, and I write down the units for frequency, which is cycles per second. And then I realize, oh, I'm making a mistake because these units don't cancel, and to give me the result I want, which should be in terms of meters per second. And so then I notice that in order to balance this equation so that the units are meters per second, I notice that I need to multiply that by radians per cycle. And so, since I was taught modified unit analysis, I know that radians per cycle 2 pi has units of radians per cycle. And so, so I can tell from this, so I know I can plug the 0.05 into here, and I know I can plug the frequency into here, and I know that I can plug 2 pi into my equation and be quite confident that I got the right answer. And so you know 0.5 times 2 is equal to 1 times 2 pi is equal to 2 pi meters per second. And so you do all this. You check your units to make sure that everything, this cancels that, this cancels that. We end up with meters per second. And so now you're quite confident that you're writing down the right answer for this question. And then you get your test back, and of course you get a check mark. And because you showed your work so nicely, you also get a nice smiley face. So now looking at this, you can see that we could take this 2 pi and group it with the frequency term and write this equation, which is what you should have done in the first place, but somehow because you're panicking writing a test, and some people get really nervous when they write tests and you forget that this is angular frequency, which is supposed to be in radians per second. And so you can take this equation here, you could group the frequency and the 2 pi and write this equation, or alternatively, you can group the 2 pi with the radius term and write this equation. And so you would write velocity equals lambda times frequency, and this frequency has unit cycles per second, and this lambda is the circumference of the circle with units meters per cycle. And so this could go either way, whatever is easier for you to remember. But in the own particle model, I am really trying to avoid radians as much as possible. And so I prefer to write the tangential velocity equation like this, with the knowledge that this lambda symbol can either mean the wavelength of a wave, or it can mean circumference of a circle. They are equivalent, and that's why I would, use one symbol for both the wavelength and the circumference of a circle in the ohm particle model. So as you may recall, the tangential velocity of the spinning ohm particle model is the speed of light, whether it be the electron or the proton or whatever other particle I am modeling using this model. Okay, so this is why the tangential velocity is really important, and it's really important that we get the right answer. And so it is my opinion that modified unit analysis is more complete. Okay, it's more robust, it's more complete than standard unit analysis. In standard unit analysis, both cyclic frequency and frequency have the same units, and wavelength, circumference of the circle, and radius all have the same units. And so modified unit analysis distinguishes between these two, and that actually makes it easier to not make a mistake when trying to solve a problem like this. Okay, so it actually, it might help someone. I believe as a teaching tool, modified unit analysis could actually be very useful, especially for people that are starting out, that aren't as savvy as others that are out there. And it might help them get a check mark instead of an X on their test. So I know there are quite a number of people out there that are starting to see the beauty in what I'm doing here. There are others that are skeptical and others that think that is actually wrong for me to do what I'm doing here. And so it is my opinion that those people are wrong. The people that think I'm wrong are actually wrong, because there's actually nothing wrong with what I am doing here. I'm just, in my opinion, I'm adding things into unit analysis that should have been there in the first place. And so modified unit analysis, in my opinion, is more complete than standard unit analysis, and it allows me to distinguish between cyclic frequency and angular frequency, and between wavelength, circumference of a circle, and the radius of a circle. So I think that this is important. I think it's important to be allowed to do this. I think it's important to understand why I am doing this. I am doing this to come up with a better language, to come up with a language that's less confusing and more robust, more understandable, more clear than the current language that we have been, living with for the last, maybe 100 years. So it's also important for the ohm particle model, which actually emerged from my approach to unit analysis, to modified unit analysis. So the ohm particle model actually came out of, emerged from, was birthed from my approach to modified unit analysis. And so, it gave me the idea to do everything in the frequency domain and to try and sort out all of the gobbledygook from the standard language, and get rid of things that I didn't need and just use things that made sense for this model. And so this model is actually very simple and can be applied to many things. And I will get into this in more detail as I continue my research. And so that's it. Have a good day, and I'll be back.